Okay, so the microphone is back working, I think. So hopefully you hear me a little bit better today. Got fixed about a month faster than I expected it to. The construction noise, however, is still going on, as you can hear. It was supposed to be done the first week of the semester, and we're going to probably finish with all this. So that's just the way it goes here. All right. So today we're going to finish chapter 8, which is the chapter on gases, and then on Thursday we'll, believe it or not, start the very last chapter in the whole course, which is going to be on liquids and solids. The third exam is a little bit strange in that it only covers part of chapter 9 as opposed to three full chapters, which I'm sure you don't mind, but I'll have to make sure I'm clear when I give the lecture about where the stopping point is. But it won't be until probably end of Thursday or probably early next week that we'll get through the exam material. So we have a little bit more to go before then. All right. So what I wanted to cover today in the Try Hard Tuesday section of the course is some interesting insight that I got from the last time I taught the course. It's not as relevant, I suppose, to you guys because the homework has changed. So just a little bit of background. It used to be when we had homework assignments in this course, you got 4 full attempts. So it was 12 questions and you got 4 attempts and you just your best score counted. You often got different questions every time, but you only got 1 attempt at each question for each try. Now it's a little bit different, obviously, because you get multiple attempts on each problem, and you typically would only use multiple attempts if you get it wrong the first time. So it's harder to analyze the data in terms of how much effort you're putting into the homework. It's also not as meaningful because of the way it's set up, even though I think it is better overall. But just to give you some insight from from 2 years ago when I last taught this course, and the question of does my effort on the homework actually matter? We think it does, but you may not believe us. So what we were able to do that semester, which was a lot easier and more straightforward, was just track how many homework attempts each student did per week. So I just broke it down into sort of a binary categories. One that was students that did all 4 attempts every week, that was the maximum, and then one that was the students that didn't do that, because that was sort of what we asked. And at that time, anyway, the bonus points that we got were tied to your homework attempts. Or at least that's how I did it. As I said, no longer makes sense to do that here, which is why we're doing the quizzes. But just look at the data from that semester. There was roughly 1/6 of the class, 18%, that was actually doing all 4 homework attempts every week. The rest of the students were falling short of that at least one time, but most of them, the rest of the class averaged about 2.5 or 3 attempts per week. So they were falling a little bit short of that. Now, for the students that did all 4 of their homework attempts every week, they had an exam average right at 69, which was at that time anyway in the B minus range. A little bit less forgiving at that time. At this point, you might be able to get to a B with that exam average. And there was about 18% of them that were in the range of failing the course with a D or an F. Versus the students that did not do all their homework attempts every week, that was the rest of the 100%, 82%. Their exam average was about 8% lower. Their average grade was over about a full letter grade below that, and there was about 38% of them that were in danger of failing. So quite a big difference in the outcomes. If you like statistics, I did a t-test on these, and there is a very statistically significant difference between the two groups, so it's not just in the noise. And so it does show that the weekly effort that you're putting in, which I hope we've all figured out and by now is important for how you're going to do on the exams and what your grade will be. So that was easier to track back then. These days, like I said, it's hard for me to do. So you kind of have to internally ask yourself if you're putting in a good amount of effort on the homework and actually using it as a learning tool as it's designed. But I think if you are, then that would be helpful to your exam performance, I think. All right, but back in with the course material. So the last major topic with chapter 8, the last major topics I should say that we're going to cover today, a lot of it deals with the behavior of gases at the atomic and molecular level. So if you have a really good memory and you remember the second day of class when we started talking about chemistry for the first time, I introduced briefly the scientific method and how scientific information is gathered and systematized. And we talked about the difference between a law and a theory. So a law tells you what happens and very often has equations associated with it. So a huge topic in this chapter, of course, was the ideal gas law, which has the PV equals nRT equation that we used a lot in recent weeks, in recent days. And then, so that's the law that tells you what happens. That's how ideal gases behave. We also had Dalton's law of partial pressures, which is a spinoff of that. Today we're talking about what's called the kinetic molecular theory. And if you recall, a theory is something that explains a law. It tells you why it happens. So the law tells you what happens, the theory tells you why it happens. And in chemistry, usually the theory involves the behavior of things at the atomic and molecular level that would then explain the macroscopic observations that we make. So that's what the KMT, kinetic molecular theory, does for gases. So there's different ways of breaking it down, but there's basically four main things you have to understand about this theory that explains how gases behave. So the first is that in a sample of gases, we assume that the particle volume, the volume that the atoms or I think someone's not muted on Teams. We could check. A little background here. So the particle volume, that means the volume that the actual atoms and molecules occupy, is assumed to be zero. Now, that doesn't mean that they don't have mass. So what basically the way that this theory works is that the gas particles, again, particles means atoms or molecules, depending on what substance it is, gas particles are treated as point masses, meaning they have mass, but they don't have volume. So in other words, a sample of gas, the volume, the volume is all empty space. The volume is not taken up by the atoms and molecules themselves. As we'll see, that's not entirely true, as you might already recognize, and that causes some deviations in certain conditions. But in a typical sample of gas, the vast majority of the space is empty, and the volume that the actual molecules or atoms make up is close to zero. Probably the most important one for us to understand, and we'll talk in more detail about today, is that gas particles are in constant motion. And more than that, it's constant random motion. So there is no specific path they take. They're just buzzing around randomly and running into each other. And an important point that we're going to elaborate more is that we've talked a lot about pressure. It's one of the key properties of gases that you need to understand. And collisions of these particles as they're moving around with the walls of the container is what causes pressure. All right, so the gas molecules are flying around randomly. They're running into each other, but then at some intervals, they're going to run into the walls of the container, and that's the force then that results in the pressure that you experience. The third one is that the particles exert no forces on each other. This one, as we will also see, is not entirely true. So all theories have their limitations and are going to be more or less true depending on the situation. So this is one that will, in certain situations, break down, saying that the gas molecules or atoms have no forces on each other. They're not attracted to each other, not repelling each other. Again, they're just zipping around and colliding in sort of an elastic fashion. So they're kind of like a bunch of marbles just flying around everywhere. They'll hit each other once in a while. They'll bounce right off each other, but they're not going to stick to each other, or they're not going to actively repel each other. All right, and then finally, another one that we're going to talk about in more detail today is that, so most of these we will cover in more detail. This is just the introduction of it. The average kinetic energy, so that's a physics term, but you're probably familiar with it at least a little bit. The average kinetic energy of the particles is proportional to the temperature. For that to be true, the temperature has to be in Kelvin. And what we're going to talk about on the next slide and sort of how this affects pressure is that as you raise the temperature, the molecules or atoms are going to move around faster. That gives them higher kinetic energy. So that causes two effects on the pressure. So when you're talking about the collisions of the molecules with the walls of the container, and that results in pressure, there's two things that affect that. One is how strongly are those molecules on average hitting the wall of the container. So if they're moving really slow, they're going to just sort of gently hit the wall of the container, not exert much force, versus if they're moving a lot faster at higher temperature, it's going to be a large collision and cause a higher force on average. The other thing that matters is how frequently they're hitting the walls of the container. So if they're moving very slowly, once in a while, they're going to bounce off the wall of the container, come back, hit it another time, very infrequent collisions, relatively speaking, versus if they're buzzing around really fast at a higher temperature, really fast collisions with the wall, very often collisions too. So those are the two things that are going to affect how many collisions are happening. One is when you go to a higher temperature, you're going to have more frequent collisions with the walls of the container. That's going to affect the pressure that you feel. And because they have higher kinetic energy, those collisions on average are going to involve a larger force. Okay, so those are the two things. This explains how temperature affects that. We'll talk about some other things about that in just a second. Okay, so those are the sort of introductory parts of the kinetic molecular theory. Now let's talk in more detail about that. And then how do we sort of rationalize some of the ideal gas laws with this theory? So the first thing is let's talk about the relationship between pressure and volume. So from the ideal gas equation, pressure is equal to nRT times 1 over V, which means that from Boyle's law, as we already talked about also separately, pressure and volume are inversely related. Okay, so let's talk about what happens. This is a diagram here that shows as we decrease the volume. So if we decrease the volume of a sample of gas, if we're keeping the temperature constant, the gas molecules on average are still going to be moving the same speed with the same kinetic energy. We'll talk those more quantitatively in a little bit, but remember, the only thing that affects how fast the gas molecules are moving is the temperature. If you're not changing the temperature, they're going to be moving the same speed, same kinetic energy on average. But if we decrease the volume and the gases have less space now to occupy, they're going to hit the walls of the container more frequently because it's a smaller space. And so on average, they're going to be closer to the walls and they're going to hit the walls more frequently. So when you decrease the volume, the collisions of the gases with the walls of the container become more frequent. And because there's more frequent collisions with the walls of the container, the pressure will increase. Again, there's two ways to increase the pressure. Either the collisions are faster, more violent, more force involved, or they're more frequent. So when you just decrease the volume, you're not changing how fast they're moving, but you are changing how frequently they hit the walls of the container. And then if we talk about pressure and temperature, this follows exactly from what we talked about in the last slide. So rearranging the ideal gas equation, pressure is equal to nR over V times temperature. So this is not one of the named gas laws, but it tells us that pressure and temperature are directly related. If we increase the pressure, we increase the temperature and vice versa. So if the temperature goes up, both of those things are going to happen. The particles are going to be moving faster when we increase the temperature. Remember, that's the only thing that can affect, on average, how fast they're moving. So temperature increases the speed or kinetic energy of the particles. So that leads to then really two effects that influence the pressure. The collisions become more frequent because they're moving faster, so they're going to hit the wall more often, and each average collision is more forceful because there's more kinetic energy involved. So both of those together lead to the pressure going up. All right, so with temperature increases, both things happen. You're moving faster on average, and because they're moving faster, they're going to hit the walls more frequently, and that's going to both contribute then to the pressure being higher. All right. Next one we'll talk about is Charles's law, which is the relationship between volume and temperature. So if you forget what it is, you can rearrange the ideal gas equation in this way. And this tells us that volume and temperature are also directly proportional. So this one, a little bit hard to think about, but if we're keeping things at a constant pressure, so what this diagram is showing is that we have weights on top of the gas that are basically fixing whatever the constant pressure would be. So in this case, the same weight is on top of the gas in both samples before and after to those little masses on top. So what that means is that if we increase the temperature of the gas, as we talked about, the collisions become more frequent and more forceful. So if you want the pressure to remain constant, the volume has to expand. So basically, these are going to start pushing harder on this movable top surface. That's going to move it up and expand the volume. So volume increases to keep the pressure constant. If it was a fixed volume, the pressure would have to increase when this happens, as we talked about in the last slide. Here, we're allowing the volume to expand. And because the particles are going to start pushing harder on that top surface, they're going to move it up. It's a movable piston, and it's going to expand the volume. All right, and then the last one is Avogadro's law, which is volume and number of moles. So again, here we're keeping the pressure constant, so you can see all these samples have the same weight, same mass on top of the gas, which is what's regulating the pressure in this simple setup. So for Avogadro's law, it's volume and number of moles. So they're directly proportional also. So when you increase the number of moles of gas, you're adding more gas to the container. We're not changing the temperature in this situation. So because it's at the same temperature, those gas molecules on average are going to have still the same kinetic energy. But because we have more gas, because we're sort of squishing more in there, we have more in the same volume, we're going to have more collisions, or the collision frequency is going to be higher. So again, two ways to sort of affect the pressure. In this case, if you're just adding more gas and you're keeping the temperature the same, you're not going to increase the kinetic energy, but you will increase how often the gas molecules hit the walls of the container because there's more of them crammed into that same volume. So as a result, the volume has to increase to maintain a constant pressure. Same story as the previous one, but in this case, because we're not changing temperature, we're not changing how fast the molecules are moving, but there are going to be more collisions. So that's going to push up harder and increase the volume. All right, so those are some things to think about now that we kind of understand a little bit at the molecular level. And again, the two key concepts are that there's really only two things that affect the pressure, the force that's exerted by a gas: how fast they're moving, which is only dependent on the temperature, and how often they hit the walls of the container, which also is going to depend on temperature, but can likewise be changed if you're changing the volume of the sample or if you're adding more gas to the sample. It's just how often they hit the walls of the container is going to matter. So let's talk a little bit more about then the molecular speeds that gases have. How fast are they moving? And the reality is that when you have a sample of gas at a given temperature, there is going to be a distribution of speeds involved. They're not all going to be moving exactly at the same rate. Some of them are going to be moving slow, some of them are going to be moving fast, and so there's going to be a range of values. So that's the first thing to understand about molecular speeds. There is no single value that you're going to have. We're going to talk about statistical averages. That's the number that gives us the most information. But there's always going to be a range or distribution of molecular speeds in any sample of gas. So if we look at how this looks, we've kind of already talked about the idea that the temperature is related to the average kinetic energy. So we kind of said simply that, I mean, a little bar means average in this context, a little bar above it. E sub k is kinetic energy. So in this context, we kind of made the simple statement that if you increase the temperature of a gas, they're going to move faster. Now, again, because there's a distribution of speed, it's not quite that simple because there's not just one value for the molecular speed. They're all going to be in a range. So what it kind of looks like, we're going to plot here the fraction of molecules that are at a certain speed, abbreviated as either U or V, in different contexts. So if you're at a low temperature, it's going to look something like this. It's going to be a relatively narrow distribution with the peak or the average occurring at a pretty low value. So this is going to be still qualitative, but if we're at low temperature, it's going to look like that. If we increase to what I'll call a medium temperature, what's going to happen is the distribution is going to be broader. If we have the same amount of gas, the area under the curve has to be the same, but we're going to broaden the distribution and shift it out towards higher values. So in green, we'll diagram a medium temperature. And then in red, if we go to a higher temperature than that, again, you're going to broaden further and shift it out further to the right. So this is kind of what it looks like. As you increase the temperature, you broaden the distribution of speeds, but the average or the most probable speed is going to be the one that is going to shift further and further to higher values as the temperature increases. So remember that kinetic energy is equal to mass 1/2 mv squared. So the average kinetic energy will be 1/2 times the average speed squared, velocity squared. And so that average speed, which is more or less the peak, it's not exactly that because the distribution is not perfectly symmetrical, but nonetheless, it's close to where this peak value is. That's going to shift to higher and higher values as you go to higher temperature. But then let's think about, let's say we're at a constant temperature. So this is really the only, we'll give the specific equation a little bit, although we're not going to really use it numerically too much in this course. But basically, the kinetic energy only depends on temperature. It's not proportional to anything else except for temperature in the sample of gas. So if we keep gases at the same temperature, the average kinetic energy will be constant. So then let's talk about what happens if we have different gases involved. So let's do O2 in blue, helium in green, and hydrogen in red. All right, so this equation here says that if they're all at the same temperature, they're going to have the same average kinetic energy. But that kinetic energy is a function of both mass and velocity. So if all three of these gases have the same kinetic energy, that means that the one that has the higher mass has to have the smaller average velocity, and the one that has the smaller mass has to have the higher average velocity. This is all constant here, but it's a product of two things. So what that tells us is that if we have oxygen, which is the heaviest of these three, the molar mass of oxygen is 32, it's going to have a distribution that looks something like this. For helium, which is in the middle, atomic mass is 4 for helium. It's going to be shifted towards higher values. So they all have the same kinetic energy, but their distribution of speeds will be different because kinetic energy is a function of mass and velocity. And then hydrogen, which is the lightest gas in the world, molar mass of 2 is going to be shifted even higher than that. So if you're at the same temperature, kinetic energy is constant, but that means the lighter gases will have the higher average speed. All right, so all three of these at the same temperature, that's key here, same temperature, all three will have the same average kinetic energy, but they won't have the same average speed because kinetic energy is a function of mass and velocity. So it's important to understand that. That one gets kind of lost sometimes, the difference between kinetic energy and velocity and how that depends on temperature. So we'll want to make sure you remember that. All right, so let's go ahead then and derive the equation that relates molecular speed and temperature and other factors as well. Now, these equations we're not really going to use in this exact form, so you don't have to really memorize them, but I suppose just giving the mathematical part of it, I hope will help you understand things a little bit better conceptually as well. All right, so more specifically, the average kinetic energy, let me write it as E sub k, keeping consistent with what I did before. The average kinetic energy is equal to 3/2 times the universal gas constant R divided by Avogadro's number times the temperature. Okay, so as you said, kinetic energy is proportional to temperature. To make it an equal sign, you put some constants out front, which is a 3/2, the gas constant R, and then Na here is Avogadro's number. So in this case, we're dividing by Avogadro's number, which means this would be the average kinetic energy of one of the atoms or molecules of that gas. Not for a whole mole, but for one of those individuals. That's what the Avogadro's number in the denominator tells you. Now, we also know, as we said in the last slide, that this average kinetic energy can be stated as 1/2 times the mass times the square of the average velocity. I'll write out all the terms here. So T is temperature in the first equation, M is the mass of the particle, again, the mass of one atom or one molecule of that gas. And then this V squared with a bar above it is called it's the average of the squares. It's a little bit different statistically than taking the average and squaring it. It's the average of the squares. So don't get too bogged down in the stats part, because we don't require stats as prerequisite for this course, and I never even took it myself, so I'm not going to be the authority either. But it's the average of the squares of the molecular speed. Whenever we have a little bar above it, that's what we're talking about. So what we can do then is we can set these two equations equal to each other to come up with an equation for average speed that's in terms of the mass and the temperature. So if we have 1/2 mv squared, we're going to set it equal to 3/2 times R over Avogadro's number times temperature. Those are the two equations for kinetic energy that we have. One thing we can do is we can just rearrange by cross multiplying. So 1/2 times Avogadro's number times the mass times V squared is equal to 3/2 RT. And then if you remember things that we would have learned back in chapter 5, if we take Avogadro's number and multiply it by the mass of one atom or molecule, that would be the mass of an entire mole of that substance. If we have Avogadro's number, atoms or molecules, multiplied by the mass, that tells us the mass of one mole, which we called MW, or molar mass. So then we can rearrange this equation and solve for the average speed squared, which is 3RT over Avogadro's number times the mass. We said that that equals molar mass. So 3RT over the molar mass. And that means the what's called the root mean square velocity, VRMS, which is the square root of the average square, is going to be 3RT over the molar mass. So a pretty simple equation that tells us that the average speed, which is called the root mean square velocity, it's really the square root of the average square. It's more complicated than just average, but we can, for our purposes, just call it the average speed. It's equal to just 3/2 RT, which is so the temperature, the constant, and then divided by the molar mass of the gas. So it's really a pretty simple relationship altogether. Now, we're not going to really use this equation in this exact form. We're going to derive another one later on that's more useful and more commonly used. But I do want to give you just one example of this equation so we can kind of just get an idea of how fast our gas molecule is moving under typical conditions. So if we have the RMS speed for argon gas at 17 degrees Celsius, roughly yesterday's or high temperature, I guess 2 days ago. So, relatively cool spring day in Houston, 17 degrees Celsius. How fast on average would the molecules be moving, or the atoms in this case for argon? So we're going to use that same equation, VRMS. Now, as I said, this exact equation is not going to really come up in your homework assignments or tests. But we do need to be a little bit careful with units here. So there are two values of the universal gas constant R. And whenever we're dealing with energy, velocity, speed, stuff like that, more physics-based stuff, we want to use the other one, which is joules per k-mole. So 8.314 joules per k-mole, not the more familiar 0.0821 that you guys have been using a lot recently. So that's the value of R we want to use. Temperature has to be in Kelvin. So we have to take 17 degrees Celsius and add 273 to that. So we want to use 290 for the temperature. And then the molar mass in this case, because we're using a gas constant that has joules in it, joules is an SI unit, and the SI unit for mass is not grams but kilograms. So our molar mass needs to be in kilograms per mole. Don't write equals yet. So from the periodic table, the atomic mass of argon is 39.95 grams per mole. But for this equation, we need it in kilograms. That won't matter later on when we derive a form of the equation that's more commonly used for us. But for now, because we just have SI units and molar mass only appears once, it has to be in kilograms per mole. All right, so we can just plug everything in then and see what number we get. So 3 times R, which is 8.314. Temperature of 290 in Kelvin, and then divided by the molar mass, which is 0.0395 in kilograms per mole. 3995, sorry. So we just get a number of 426 meters per second, which is very fast. I always forget. I think we're more familiar with like miles per hour from stuff like driving. I think if you want to take meters per second and convert it to miles per hour, I always forget if you divide by 2 or multiply by 2. It's approximately that, but it's a big number. So this is pretty fast. We're just at a regular temperature, and the gas molecules are moving around faster than you should ideally be driving, let's say. So probably faster than you're capable of driving if you have a regular car. So it's pretty fast. So that's just a demonstration of, we talked about gas molecules being in constant random motion, and that motion at normal temperatures is pretty fast for us, 426 meters per second. Let me do that conversion real quick so I can give you the real number. 426 meters per second to mph. So it is about double. So in miles per hour, that would be 953 miles per hour. So almost 1,000, faster than commercial airliner would travel, for example, faster than the speed of sound. So gas molecules are zipping around. That's the whole point of this exercise. So this form of the equation works, and it gives us the root mean square velocity, but it's not really one that we're going to actually use. We're going to relate this, though, to some other behaviors of gases that are going to rely on this same constant and the same concept, and that is going to be what's called Graham's law of diffusion or diffusion. So this relates to similar behaviors, which is effusion and diffusion. So we don't want to know the definitions of them, but the equations are all the same regardless of which one we're talking about. So effusion is the escape of a gas through a small hole. Say a tiny hole to make it more descriptive. You can think of effusion as the leak rate. So gas leaking out of a container, how fast does that happen? So if you have a small hole in your container, how fast is it going to leak out? That's diffusion. Diffusion is the movement of a gas through another gas. So as an example of this, if I were to take, you guys have probably all smelled natural gas before, right? What you're actually smelling is not the natural gas. It's a little bit of a sulfur compound that they put in a natural gas so that you can smell it, because natural gas itself is odorless. So that stuff is really nasty. You just need a tiny amount of that to be able to smell it. So if I were to take a little part of that and release it at the front of the room, at some point, the people in the back of the room will be covering their noses, right? So that's because of diffusion. Whenever you have molecules of gas, they're going to move through the space that they're in. They're not going to just stay there. They're not going to just be sort of hanging around. They're going to spread out, as you said, occupy the full volume. And so diffusion is the movement of gas through another gas. So two slightly different behaviors or concepts we're talking about, but they're all related by the same equation, because the rates of effusion and the rates of diffusion, how fast a gas leaks or how fast it moves through space, are both proportional to the average speed. So if the gas molecules are moving faster, they're going to leak faster. If the gas molecules are moving faster, they're going to travel through space faster. That one makes even more sense. So what we can do is we can take that equation that we just derived and write it as a ratio. So if we're comparing two different gases here, it's going to be, for the rate for gas A is going to be 3RT over its molar mass, and the rate for gas B is going to be 3RT over its molar mass. And if the two gases are at the same temperature, which is really the only conditions where it makes sense to compare them, we can then rearrange this equation and say that it's equal to the square root of the inverse square root of the ratios of the molar mass. So it'd be B over A. Because the molar masses are in the denominators on both of these, so when you simplify the fraction, they end up inverted, where rate of A over rate of B is equal to the molar mass of B over the molar mass of A. So this is sort of the standard form of this Graham's law equation. And so the nice thing about this is if we're comparing two different gases and talking about either their leak rate or their diffusion rate, you just need the molar mass. That's the only information you need to do that if they're at the same temperature. It also means that the molar masses don't have to be in kilograms anymore, because it's a ratio of 2. So as long as the units are the same in the top and bottom, they'll divide out. Okay, so that's the Graham's law of effusion or diffusion. Now, there are a couple of variations of this that we want to be familiar with in terms of how the problems can be phrased. In most cases, that doesn't change the equation, although in one case it does. So remember that we're talking about here a rate or a speed that these are occurring at, which is a ratio of distance over time. So if we talk about a Graham's law problem where we're talking about the how far the gas traveled. So if we say one gas traveled 2 meters in this period of time, while the other gas traveled 5.2 meters, talking about how far they're going. Well, that's going to be proportional to the rate that they're moving. So in that case, the equation doesn't change. The distance that one gas travels over the distance that the other gas travels is still equal to the inverse square root of the molar masses. So it'd be B over A on this side. So in that case, the equation is the same as the sort of standard form, which is in terms of rate of diffusion or diffusion. Now, the only time that this changes a little bit is if we're telling you the amount of time that it takes. So if we say that this gas diffuses or leaks in 2 minutes and the other gas diffuses or leaks out in 3 minutes, or we're saying this gas takes 1 minute to travel across the room and this gas takes 5 minutes to travel across the room. If we're framing it in terms of the amount of time that it takes for one of those to happen, rate and time are inversely proportional. And so that means we have to flip one side of the equation in order for that to work. So if we're doing it in terms of the amount of time that it takes gas A to effuse or diffuse over the amount of time that it takes for gas B, we have to flip the other side of the equation to make it still work out because time and rate are inversely proportional to each other. So in that case, it's the direct square root of the molar mass ratio is A over B. So we do have to remember to flip the equation sometimes only when we're talking about the amount of time that it takes for a gas to effuse or diffuse. Thinking about it conceptually does help to make sure you don't mess that up because if a gas is lighter, it's going to be moving faster, which means it's going to have a smaller time. So they should be, in that case, directly proportional to the molar mass. All right. So those are the different variations of the equation. Let's just see then how they're used. So one way we could talk about it is just in terms of that ratio of their effusion rate. So we have equal molar, same amount of moles of hydrogen and helium. Which gas effuses faster and by how much? So we're talking about just the relative rates of effusion or diffusion. We're just going to be computing this ratio. Doesn't matter which order we do it in. We can do rate of H2 over rate of helium, or the other way around. It doesn't matter which way you compute it. And just to determine whether the ratio is larger than or smaller than 1 is going to tell you whether the denominator or the numerator is diffusing faster. So because it's in terms of rate here, it's going to be inversely related to the molar mass square root. So we're going to have helium on the top under the square root and hydrogen on the bottom if we're writing the and so then what we end up with is we just put those numbers in. So under the square root, we have the molar mass of helium is 4. And here we can keep it in grams per mole because the units will divide out as our ratio. And then 2.02, which is hydrogen on the bottom, which is the square root of 1.98, which is 1.41. That tells us that H2 effuses 1.41 times faster as this problem is asking. Because the ratio of the two rates is 1.41, it's bigger than 1. That tells us hydrogen is moving faster than helium. A lot of students ask, well, how did you know to do hydrogen over helium? Well, I didn't. I guess I knew because I made the problem, but in reality, I wouldn't know that at the beginning of the problem necessarily. So if you did it the other way, that's totally fine. So we could have also done the rate of helium over hydrogen, which means we also would have to flip the other side of the equation. So then you just get the reciprocal of this number. Which I don't remember exactly what it is. Somewhere around 0.71, I think. Give me a second. I didn't actually do this before. I just thought to do it now. So it's like, yeah, 0.709. We'll do 3 sig figs. All right. Now, because that number is smaller than 1, that tells us that the rate of helium is smaller than the rate of hydrogen, which answers that part of the question. If you want to get how many times faster is hydrogen, you still would have to take the reciprocal of this. So you could have started here. You would have come to the conclusion that hydrogen is moving faster than helium. but then you'd have to take the reciprocal to get how many times faster hydrogen is moving. So you can start the problem either way. You may not know that right off the bat, but it works out in both cases. All right, so let's do a slightly different one now. Any questions on that before I move on? All right, slightly different one where we're going to take, this time we're comparing helium to ethane, C2H6, which is a minor component of natural gas, not the major component, but it's found in there. So we have, it takes 1.25 minutes for 0.010 moles of helium to fuse. How long will it take for the same amount of ethane? So this is one where we're giving you the problem in terms of time. Now, I suppose you could calculate rates by taking the amount of helium that's effusing or diffusing, sorry, effusing in this case, and then dividing it by the time. But the simpler way is just to use the times directly because we're talking about the same amount of gas in both cases. So we want to do it in terms of time. We want to calculate the time that it takes for one of the gases. And again, which one you put in the top and the bottom is sort of irrelevant. This way makes the algebra a little bit easier, as we'll see. So if we want to do it in terms of the amount of time that it takes, that's going to be the amount of time that it takes for C2H6 is what we're looking for. So that's our unknown. For helium, it's 1.25 minutes. And that's going to be now directly proportional to the square root of the molar masses. So it's going to be the molar mass of C2H6 divided by the molar mass of helium. So remember, when we're doing it in terms of time, that's the one time that they're going to be directly related to each other. So if we have C2H6 on the top of this ratio, C2H6 will also be on the top of that ratio only when we're dealing with the amount of time that it takes for a gas to effuse or diffuse. So we can put everything else in. So the time that it takes for C2H6 to effuse over 1.25 minutes, now we have just the 2 molar masses to put in. So the molar mass for C2H6 is 30.08. The molar mass for helium is 4 again. And so then we just have to cross multiply. So we take this ratio, take the square root, cross multiply the 1.25 minutes over. And so the time that it takes for C2H6 is 3.43 minutes. All right, so the algebra might be a little bit different than we're used to, but it's not too bad. Whenever you have two things under a square root, you just take the ratio and then take the square root of the whole ratio. That works out mathematically just fine. And then we just cross multiply by the 1.25, move that over, and that'll give us the time in the same units of minutes. All right, so it is a heavier gas, so it is useful to think about these questions conceptually. Heavier gases move slower, so they should diffuse at a slower rate, meaning it should take longer. So if you got a number that was smaller than 1.25, it likely means you inverted one side of your equation. Because this is the heavier gas that we're talking about, it should take longer for it to diffuse than the lighter gas. All right, any questions on that? All right, last example problem on this topic. Here we're talking about the amount of gas that it fuses. So, where's that problem? All disorganized here. All right, if 7.23 milliliters of an unknown gas diffuses in the same amount of time as 13.8 milliliters of argon under the same conditions, what is the molar mass of the unknown gas? So same equation, same relationship. It just requires us to solve for something that's different. So we're talking about the amount of gas that effuses. That's proportional to the rate. So we're going to use the standard form of the equation. So the rate of argon over the rate of our unknown gas. And you can write it in either way. This way it makes the algebra a little bit easier, but if you did it the other way, you'd still get the answer. And that's going to be equal to the square root of inverted this time, molar mass of X, which is our unknown, divided by the molar mass of argon. So now we just have to put the numbers in that we know. So these numbers here are proportional to the rates because it's the same amount of time. So we can just use those numbers directly in the ratio. So for argon is 13.8 milliliters. For the unknown gas, it's 7.23. And then if we have the whole thing under the square root like this, you can also write it in this way. Hopefully this is obvious, but if you've not done this type of algebra in a while, you can also write it in this way. So you're going to have, in the numerator, you're going to have the unknown molar mass. In the denominator, you're going to have the molar mass of argon, which is 39.95. And then to do this algebra, you would I'm not going to do all the intermediate steps here, but basically you would need to square both sides to get rid of the square roots. And then that means that the molar mass of our unknown gas is going to be, when we cross multiply and divide, or just cross multiply in this case, no division involved, 13.8 milliliters over 7.23 milliliters. That whole thing squared times 39.95, which is the molar mass of argon. So that's the algebra, and that comes out to 146 grams per mole. And again, checking that our answer makes sense, this gas is diffusing slower, less of it leaks out in the same amount of time as the argon, so it should be heavier. So you should get a number that at least is bigger than that. If it wasn't bigger, again, it probably means your math was, or your equations were off. So a little bit of algebra that we haven't seen before, but with square roots, you just square to get rid of them and cross multiply to get the answer you want. So any questions on the problem itself or the algebra? All right. And then, yes, sure, go ahead. All right. So then the last thing on this topic really is something that whoever's taking the lab, have you guys done this experiment yet? All right. So it looks familiar. And now you kind of already know what I'm going to talk about. If you're not in the lab, if you haven't taken it yet, then the way that this is a sort of common diffusion experiment to sort of show how diffusion works. So what you do is you take aqueous ammonia, NH3, on one side. You sort of have a wet cotton ball with that on it. And then you have another wet cotton ball that has aqueous HCl on it. Not the world's safest experiment, but I guess if you're careful, it's not too bad. So you have basically, and then the dissolved reactants are both gases. So some of the NH3 is going to diffuse out of the cotton ball into the glass tube, and from the other direction, some of the HCl, which is also a gas, is going to diffuse from the other side. So they're going to meet somewhere in the middle, and when they react with each other, they form ammonium chloride, NH4Cl, which is a ionic compound that ends up as a solid. So two gases come together and react, and they form a solid that you can then see as a little white ring, ideally. Now, I've heard this experiment doesn't work very well, but I haven't actually done it myself, so you guys can correct me if I'm wrong. But and this is sort of how it works. So to write things a little bit bigger for you, you have NH3 on this side, HCl on that side. The gases are going to diffuse towards each other, and somewhere in the middle, they're going to meet, and they're going to form NH4Cl when those two react with each other. All right. So this is kind of like a problem, the classic physics problem. If a train leaves Chicago going 55 miles an hour and a train leaves Cleveland going 63 miles an hour, and the two are, what are they, about 180 miles apart, where will the two trains meet each other? It's kind of like that type of problem. You have two gases moving from opposite directions, different speeds because they're two different gases. Where exactly will they meet each other? So the reaction here, as we said, is NH3 gas, HCl gas, making a solid NH4Cl. So you can see the solid. It's a white solid. And so then again, you're starting at opposite ends of the tube. The two reactants will diffuse towards each other. And then once they meet up, they're going to form the product ammonium chloride. So that's really the experiment. So you would basically, in this, you would know the total length of the tube, and you'd be then able to compute from Graham's law of diffusion, or diffusion in this case, the distance that each of the gases travels. So that's the idea. So let's just do an example of that. So we're going to do this exact experiment where we have HCl and ammonia, given molar masses are here, and the total distance is 30 centimeters, so basically 1 foot. How long does the NH3 travel before reacting with the HCl? So we have this sort of setup here. The whole thing is 30 centimeters. And we're going to have NH3 coming from one direction, HCl from the other. They're going to meet somewhere in the middle, and we're going to be looking for this distance there. So the way that this problem is set up is sort of in 2 steps. There's 2 unknowns here. We don't know either distance. We only know the total distance is 30. We have a distance for ammonia, a distance for HCl. So we do need 2 relationships to be able to come up with the first with the 2 unknowns. The first thing we can talk about, which is going to be the same for any problem we do of this type, if it's HCl and NH3, is just the ratio of the 2 distances that they travel. Again, in either order, HCl on top or NH3 on top. It doesn't matter how you start it. That's going to come directly from Graham's law. So because this is what we're talking about, the distance traveled, it's going to be inversely related to the molar masses. So we're going to have NH3 on the top under here, HCl on the bottom. So the molar mass of NH3 is 17.03 grams per mole. HCl is 36.46. To avoid confusion, that whole thing should be under the square root. So we get a number of 0.683. So this ratio is equal to 0.683, which means if we cross multiply, the distance that HCl travels is 0.683 times the distance that NH3 travels. Those are our 2 unknowns. So that's one equation in relating those 2 distances. And that is just dependent on the molar masses. So no matter what problem you're doing with HCl and NH3, whatever your total path is, that's going to be a relationship that comes straight from Graham's law. But we can't uniquely solve for those 2 distances without a second equation. But the second equation, which is quite simple, is that because the whole length of the tube is 30 centimeters, the total distances that they travel has to equal 30. Again, they're meeting somewhere in the middle, so the total distance they travel will have to be 30 centimeters. So now we have this equation, and we're going to basically replace this distance with that there. So we're going to have 0.683 times the distance that NH3 travels, and we're solving for the distance that NH3 travels, so that's the way we want to do it in this case, to be more direct. So now it becomes simple algebra. You just add these 2 together and solve for the distance for NH3, which comes out to 17.8 centimeters. NH3 is the lighter of the 2 gases, so it's traveling faster, so that means it will move more than half of the distance. If they were exactly the same, they'd be in the middle exactly, but NH3 is moving faster, so it's going to travel a little bit further before it gets to the HCl. All right, but that's really the 2 equations you need. This one comes from Graham's law. This one is just the sum of the 2 distances being equal to whatever the length of the tube is. All right, any questions on that? So if you didn't understand that in lab, hopefully it makes more sense now. And you might see problems like that in this class as well, even though it is sort of a lab topic also. All right, the final topic of chapter 8 that we're going to finish today is talking about deviations from the ideal gas equation. So the ideal gas equation is PV equals nRT, but the word ideal does mean something. It means that they're behaving in a perfect ideal way, which is not always true. In reality, is never true. So let's talk about some of the deviations then that can occur from ideal gas behavior. So with this equation, PV equals nRT, what this ideally means is that the ratio of PV over nRT should be exactly equal to 1 if it was an ideal gas. We're just moving nRT over to the other side, dividing both sides by nRT, so this ratio equals 1. So what we're going to do in this is we're going to plot, this is not going to be perfect, so I'm doing it by hand. We're going to plot PV divided by nRT as a function of the pressure of the gas, the external pressure, over a wide range. So, here we're in this room, the pressure is approximately 1 atmosphere. We're going to go all the way up to 1,000 atmospheres for this one. So what you'll see is that for a really light gas like H2, you're going to see over almost the entire range, you're going to see a slight positive deviation from PV equals nRT. So H2 would look something like this, where the ratio of PV divided by nRT is always a little bit bigger than 1. For most other gases, though, what you'll typically see is that at relatively low pressures, they'll dip down a little bit, and then they'll start going above 1. So that would be nitrogen, for example. Nitrogen has a molar mass of 28. If we go to CH4, it'll dip. Now, which of these is which is not so important, but the point is that different gases are going to behave differently, and they're going to sort of dip down to different amounts below the ideal, and then start raising up above that at some pressure. So you don't have to worry about too much about which one is which, but basically the 3 gases or the 4 gases here all behave differently. In most cases, you will see early on a negative deviation from ideal gas behavior, meaning this ratio is less than 1. And then at some pressure, it's going to cross back over and start increasing after that. So we're going to talk a little bit about why this happens. So the first part is, why do these gases at sometimes dip below PV over nRT equals 1? The reason for that is something that we're going to cover in more detail in the next chapter, chapter 9. But one of the assumptions of the ideal gas law, or the kinetic molecular theory, which describes that law, is that there's no forces between the gas atoms or gas molecules. Now, that's not entirely true. And as we'll learn in chapter 9, all substances that have electrons, so everything in the world, has some small force of attraction to other things. So these gas molecules, N2, sorry, this would be CH4, not CH2. There's no such thing as CH2. So all these gas molecules are going to have some little force of attraction between each other. So if you go to high pressures where they're forced to be really close together, they're going to start sticking to each other, which means they're not going to hit the walls of the containers often, which means they're going to exert a lower pressure than you would expect. So that's why they will sometimes dip below the ideal gas equation at these earlier pressures where the gas molecules start sticking to each other. They don't hit the walls of the container as often as they should as a result. But then at some point, and with hydrogen is really over pretty much the entire range, at some point they're going to cross over and start getting positive deviations where the ratio or the product of pressure and volume is greater than nRT. Now, why does that happen? That happens because of the other assumption from the kinetic molecular theory, which is that the volumes of the gas molecules themselves are exactly equal to 0, which is clearly not true. We know the atoms and molecules are tiny, but they take up some space. They're not 0. And so if you force a lot of them to be really close to each other at high pressures or small volumes, then what happens is the volume that the gas molecules occupy is significant compared to the total volume. And so they don't have the full available volume to move around in. And so that means the apparent pressure gets higher because they're hitting the walls more frequently because the gas molecules themselves are taking up some of that available space. So those are really the two things that cause this deviation. So then that leads to the question, which is kind of the level that we want you to know it for this course, purely conceptual for this topic, is when do real gases behave most like ideal gases? When do they come closest to following the ideal gas equation? So that's going to occur when your pressure is relatively low, because at low pressure, the gas particles are far apart from each other. So that's going to minimize those forces of attraction, which we'll talk about more in chapter 9. And also means that the volume of the particles in that situation will be much, much smaller than the volume of the container. So at low pressures, when the gas particles are very far apart, it would still be a relatively good assumption to assume that the entire volume is empty space and that the volume of the gas particles is negligible. That's going to be true when they're far apart. It also is going to be true that the gases behave more ideally at high temperatures, because at high temperature, those particles are moving around very fast. And so that they spend little time interacting with each other. As we said, they're all molecules are going to have, and all atoms are going to have some force of attraction with each other that we'll talk about in the next chapter. But if they're moving really fast, they just don't have enough time to spend with each other, so those forces of interaction are minimized. In other words, if they're moving slowly, they're going to sort of find each other and stick to each other for longer periods of time, versus if they're zipping around, they might feel each other running each other once in a while, but they're going to mostly just be bouncing off each other, and that's going to minimize those forces of interaction. So those are the two conditions: low pressure and high temperature, when gases will behave most ideally, meaning they will follow the ideal gas equation. And under regular conditions, around 1 atmosphere, around the temperatures that we deal with, most gases are very close to following the ideal gas equation. You won't really notice those deviations. If you're doing an experiment in the lab at the level of precision that we typically do it, you won't really see any obvious deviations. But if you get to really extreme conditions where the temperature is really low and the gases are close to even becoming a liquid at that temperature, as we'll again talk about in chapter 9, or if your pressures are extremely high, higher than we typically deal with in our everyday lives, in those situations, you would notice deviations where PV equals nRT doesn't quite work. So then what some scientists did is, to correct for this, they came up with what's called the van der Waals equation. And this is an equation that, I guess, since I haven't looked as closely at the new homework assignments, I shouldn't 100% promise, but I don't think you're actually going to use it. We never required you to actually use this equation in the past. I'd be surprised if that's changed. But we want again, to, as an equation, help you understand how these things work and what we've done. So what you can do to correct for real gas behavior is you can actually make empirical corrections to the ideal gas equation. These are not based on any sort of theory or any sort of systematized observation. This is really just purely empirical. It's just mathematical fitting to make the equation work better. So what you do is, instead of just PV equals nRT, you have pressure is going to be corrected by this factor here, n squared A over V squared. N and V still mean the same, but you have this other parameter A added on. And then the volume is going to be corrected by, you're going to subtract from that N times B, another parameter, and that's going to be equal to nRT. So a more complicated form of the ideal gas equation that accounts from the deviations that we sometimes see. So this term here, A, is going to be the one that adjusts for those interparticle interactions. So to account for the fact that the gas molecules have small attractions to each other, we have a little bit of a positive correction added on to the pressure. And then B here, which is the other parameter in this equation, it adjusts the volume to account for the fact that the volume of the gas molecules is not zero. This accounts for particle volume. All right. And then these parameters A and B here, which are called van der Waals parameters, because they belong to the van der Waals equation. This is not as useful of an equation because these parameters depend on what gas you're talking about. They're not universal parameters. They're experimentally determined, and the equations were really just determined by fitting as best we could to the data that we had, and they're unique for each gas. So they're not universal constants like R. They depend on which gas you're dealing with. So this van der Waals equation is not as useful as PV equals nRT because it depends on what gas you're talking about and is mathematically more complicated, obviously. But it is more accurate, especially when you get to those extreme conditions where the deviations from the ideal behavior start to matter. All right. So I guess we got a little bit early today. But if there's any last questions I can cover before we go. All right, just to give you a little bit of a preview of what's coming. So as I said, we're gonna starting next class, we're gonna move into chapter 9, the very last chapter. That one is broken up over the third midterm and the final. We will likely finish that material at least with 1 or 2 lectures to spare. So the last 1 or 2 course sessions will have. This is going to be lame. I'm just warning you guys, but there's going to be a required teamwork exercise that we have to do now. This is not my idea, the university's idea. So I'll give you more information about that via class announcements and email, so you'll know exactly when it is and make sure you're here for that, because that's how you're going to get that 1% of your grade. And we'll do some review as we have time for. So, and those two things might be kind of combined with each other, review and teamwork. So that's going to take up one of the days of class. But for now, for the next few classes, we'll be finishing chapter 9 and getting then ready for that as it comes.